no one can fault this system. This is a huge model. So basically, if you were to train it overnight, you can probably, if you want to get a good 8 hours sleep, you can probably train maybe for 3 epochs at least, maybe 4 pushing it. And you probably would get some very, very good accuracy. I'm actually going to do an experiment tonight and leave this training overnight and see what happens. If I do, in the presentation slides, I will add in a screenshot of my results after 5 epochs. So this concludes our chapter on building this famous CNN. The point of this lesson was that I wanted to show you how from diagrams like this, we can easily start recreating stuff like this here. It's quite simple to use Karas's modular system of adding layers. It's so easy to build these CNNs, and I hope this encourages you to actually experiment and build your own CNNs. Hi, and welcome to 13.3, where we talk about batch normalization. So, batch norm was proposed by these guys in 2015 in their paper titled Batch Normalization, Accelerating Deep Network Training by Reducing Internal Covariance Shift. And we're going to see very shortly what internal covariance shift actually is. So previously you know a bit about normalization. Basically it's a way of standardizing our values. So we know images range from 0 to 255, but we apply a normalization factor by dividing it by 255 to make all our values equal to being 0 and 1. And we do this so that one particular feature of data, or row of data you could say, doesn't have basically a larger influence on the training. So example of this being a problem, in images you may not foresee this happening because everything is basically pixels. But imagine you have a neural net where one of the inputs is weight and the other one is height, and the height is in feet and weight is in pounds. Weight is going to have much larger values being input, so you have to standardize those values. So batch norm, however, is used to normalize the activations of an input tensor before passing it into the next layer of the network. So you'll see what this means shortly. So remember, before we begin training, we have to initialize random weights here. But what if one of our weights randomly became very large? Just either a random chance, or maybe in some training, when it's training, it coincidentally just ended up with having an update that made it extremely large. What happens now is that this cascades throughout the network, causing other large weights and imbalances, and basically sort of messes up our training. It causes what we call instability in our training. So batch norm is applied to a layer here. So if we apply batch norm to this layer, what happens is that it normalizes the output from the activation functions of this layer. And it does this by multiplying it by a parameter and then adding another parameter to the results. And the result is that all the activations leaving a batch normalization layer will have approximately 0 mean, which is good. The weights now don't become imbalanced with extreme values, since normalization is now included in the gradient process. And this is how easy it is to add a batch normalization to a layer. So by adding it in here, it's added to the layer right before this. So this convolution layer now, the activation units will now be passed through a batch normalization layer that will normalize it. So it reduces the number of epochs it takes for our neural net to converge, which is a great thing, and it actually adds in regularization, which reduces our overfitting. However, one problem is that it slows training down significantly. Though it does improve the stability of our training, so it allows us to use larger learning rates as well. So we can sort of compensate for the speed by using a slightly larger learning rate. Okay, hi, welcome to 13.4. We're going to create a clothing apparel recognition system using the fashion MNIST dataset. So let's take a look at this dataset now. It has 10 categories: t-shirt, trousers, bags, ankle boots, whatever. And basically it's a direct copy of the MNIST in terms of images are exactly the same size, 28 by 28 grayscale, and 60,000 training examples with 10,000 test examples. So it serves as a direct replacement for MNIST. And the reason for this is because maybe about 10 to 15 years ago, MNIST sort of became almost too easy. Like the top accuracies were basically 99 point something, and it stopped being as fun to compete in MNIST. We needed something more challenging, and Fashion MNIST was developed for this instead. So let's take a look at some of the images in FashionMNIST. You can definitely see this is a pullover, a t-shirt, a shoe, a purse. Some would definitely be easy for CNN to pick out, like purses and shoes definitely have a distinct shape. Ankle boot though may be mistaken for a shoe sometimes. A dress could look like a t-shirt, depending on the shape. Basically these images look like x-rays. However, basically I think they were just thresholded and brought back, maybe blurred a bit as well. I can probably figure out how to pre-process clothes like this. Okay, hi, welcome to our IPython notebook on 13.4, which is our FashionMNIST dataset. And what we're going to do here is two things I want you to make sure of. When you downloaded the FashionMNIST dataset resources, please ensure that it's in this directory here, and it looks like this. We have FashionMNIST underscore fashion underscore MNIST, and you see these 4 files here. These are ubyte files, which we'll take a look at shortly. So to unpack ubyte files, we use this function I found on GitHub here from Tyler Nilon, let's credit him. And basically what this does is that it takes this file and gets it into this X-train, Y-train, XTEST, YTEST format directly. And it's just like the format from MNIST. So it's a very quick and easy function to use. It's super quick, I should say too. And look at this. This looks exactly like our MNIST dataset, as it's supposed to be. It's supposed to be a direct drop-in. So now let's take a look at some sample images here. Let's run this plot. This is good. A lot of times when you run matplotlib for functions for the first time, it doesn't actually show, it just tells you it is a figure size here. So you have to do this again to generate the plots. So we see our shoes, sandals, purses, pants, and coat or something. And now let's look at our approach here. So you're pretty familiar with this now from MNIST. Basically, we're just getting our data in shape and in the right format. Hot one encoding here as well. Print the number of classes just for our information. Get the number of classes, number of pixels. We use it here to create our CNN. Now, the difference with the CNN now is just added a simple layer called batch normalization. And let's see how it affects our CNN's parameter sizes. It should have 0 effect on it, and as you can see, it doesn't. So now let's train our model. It takes a while to start. And let's see, after 3 epochs, you can see how long it takes to train an epoch here. And you can see that it is much slower than it was before on MNIST, but the accuracy is pretty good. So after 3 epochs, let's see the results we get. Alright, so after 3 epochs, we've seen that we have actually gotten pretty good accuracy, 91.13%. So that's quite good after just 3 epochs on the FashionMNIST dataset, which is supposed to be much more challenging than the MNIST dataset. And batch normalization was used, and I'm pretty sure it accounted for this improvement in accuracy. I actually have another notebook running right now where we remove batch normalization, and I'm going to show you the difference after 3 epochs, how batch normalization, without batch normalization, you get worse results. So for now, let's just test this model, this 91% accurate model. Display is not defined. Actually, we don't need this display. This was an old bit of code I used before. So here we go. This is pretty cool. So it's a coat, predicted a coat. It's actually a coat. Same for the shirts. Got the trouser right, dress right. All right so far. Now you'd expect with a 91% accurate model, you would get at least 1 in 10 wrong. So let's see if we get any wrong again. So far it's all good. Okay, so that's actually quite good. Now let's see how this one is progressing. This one is almost at the end of 1 epoch. What I'll do, I'll wait for this and I'll show you guys the results after 3 epochs. Okay, so here are the results of training our model without batch normalization. And as you can see, after 3 epochs, we only got 90% accuracy, whereas with batch normalization, we got 91% accuracy. Now it seems like a small difference, but batch normalization does make a big difference overall when you're training these networks. That 1-2% extra could mean a difference between a good model and a great model. So just one thing you can observe though is that look at the time it took to train 1 epoch. Just over 2 minutes here, whereas with batch normalization, it took just over 3 minutes. So you can definitely see how using batch normalization has a price. Hi, and welcome to chapter 14, where we take a look at ImageNet and then we start using some pre-trained models in Keras. And those models include VGG 16, 19, Inception version 3, ResNet 50, and MobileNet. So the contents of this chapter, basically we're going to experiment with those models I just mentioned. Then we're going to understand a bit about the VGG family of models. Then we take a look at ResNet 50 and then understand the Inception family as well. So it's going to be a very interesting chapter. Stay tuned. Hi, and welcome to chapter 14.1, where we start experimenting with some pre-trained models. And these models include VGG, Inception, ResNet, and MobileNet. And I'm sure as a computer vision enthusiast, you've heard of some of these models before. And what we're going to do in Keras, we're actually going to use these models, these already trained models. But before we begin, let's talk about ImageNet. So what made these models famous was their performance on ImageNet. ImageNet is part of basically the ILSVRC. That's the ImageNet Large Scale Visual Recognition Challenge. And it's basically the benchmark and standard used to test modern day CNNs. Now it comprises of 1.2 million training images. It's a huge image data set into 1,000 object classes. You can see why it's so hard to get good accuracy in this challenge. This is an example of how ImageNet looks. You can go to the website. It's imagenet.org. You can see it here. And basically you can explore the different training images here. This is a summary of the last few networks that actually won ImageNet, and this is the top 5 error rate. And basically what top 5 error rate means is that was the actual image that was in the picture, like let's assume it's classifying this image here. How was his top 5 results? Like, was it in the top 5? So we do some aggregation, and basically that's how we come up with this ranking here. So you can see ResNet was actually quite successful in ImageNet, and it had much less parameters than VGG. So in the next few chapters, we're going to start talking about these models here. So what's cool about Keras is that it actually comes with these pre-trained models. We can import them into Keras and actually use and execute them. And then we can actually even tweak them, which you'll find out later, for our own models. So loading them is quite straightforward, and we're going to do that now. Okay, so let's go back to our virtual machine and no. From current slide, and then we go to this here. Okay, so welcome to our virtual machine, and let's open this chapter, this IPython notebook file, 14.1. And cool. So, like I said, we're going to use some pre-trained models. So to import a pre-trained model, this line basically is quite important. It allows us to actually access the ResNet 50 model, and then it's so easy to use after that. So we just load it here. We specify the weights we want, the pre-trained weights being the weights that were trained on ImageNet, and we just run this, and it takes a little while to load because, as you saw in the previous slides, ResNet is a huge model. It has 138 million parameters. So this one may take a bit of a while to load, but there it's finished, and now we can just load an image and just bring it into the format that we need and test it. So we just go ResNet, this is what we call our model here, ResNet_model.predict. So let's see what happens. Let's run this again. Oh, there we go. So it actually predicted that this image a dog, and let's actually find this image now. Let's go back to this directory. So the images we used here were a dog. This is actually my dog, Samuel. So it actually got it right. So let's go back to our notebook. So it actually said it actually has the breeds of the dog, which is quite cool. It basically classifies so many classes. Now here's Labrador, and it's not here. However, I'm guessing this Chesapeake Bay Retriever, sorry, just couldn't read it properly, is very close to how he looks. I'm not even sure what this is. I actually should check it out. Let's see what this is. Okay, I can see how he resembled that in that picture. That's fine. So now let's run a few test images here. We'll go through this here. I actually find this should not be here. Oh, I know why it's like this. I'll go back to this after. So let's run this through. Let's load some images with OpenCV and draw our results on our test images. Okay, so this is my wife from who beat last. Actually, this is a bikini competition she did 2 years ago, and basically got it right. 58% probability that it's a bikini. That's actually quite good. Let's see the other images here. This one is a snail, and I got it with a probability of 15%, which is quite good because everything else here, slug and a puffer, do resemble a snail. Let's see what else. Back to my Labrador. So okay, so we see it works quite well. You can now load your own images here into this folder and experiment with images of yourself or anything you want and see how close. So let's go back to our IPython notebook and see what else we can do. So how about we compare all three models on the same test images? And to do that, we have to load VGG16 and Inception version 3. And we do it exactly the same way. We just import them from Keras's applications, load the weights that were trained on ImageNet, and we just give it a name. VGG is here and Inception is here. So let's now load all three models and test them on our test images. Oh, actually I haven't run this code. I was wondering what was going on there. Okay, so again, it takes maybe about 10 to 20 seconds to load these models. ResNet definitely takes longer than the others, and the reason I'm not loading ResNet again here is because we loaded it previously here. So let's wait till this is done. Remember, it's two models we're doing at the same time now, so it's going to be a bit long. Alright, there we go, it's done. So now let's compare all three models and see how they compare. Okay, there we go. Okay, so it came up 3 times like this. So it's a bit messy, but we know what the images are. We've seen them before. So let's look at this one. If VGG16 predicted bikini, and that was definitely correct. So did ResNet. What did Inception do? Stopwatch, ashcan, and shield. I don't see any of those things in this image. So definitely Inception has some issues here with this image. So let's see what the others look like. Okay, so this is a snail. Where is the other image here? Alright, actually we can look at it here. So we see VGG said a bollard, and I didn't even show what that is. Mushroom and coral reef. Fair enough, close to a mushroom. Not exactly though, but I can see something like that looking like a mushroom. Inception again got horrible results. Chain link fence, website, that's weird. And sunglasses. So that's all definitely very off. And ResNet definitely got it right. So let's see what the other image, my Labrador, does. So VGG said German short-haired pointer. I'm guessing that's a dog, and I'm guessing Chesapeake Bay Retriever again came up here. Let's see what Inception got. So Inception definitely has some issues here. And we know what VGG got. We can just bring it up. Sorry, ResNet got. And here are the results here. So this is pretty cool. So that's how we play or we experiment with these pre-trained models. They are very much useful in doing a lot of other things later on, and you'll find out. Hi, and welcome to chapter 14.2, where we try to understand exactly how VGG16 and VGG19 actually work. So VGGNet. This model was developed by these guys here in a paper titled Very Deep Convolutional Neural Networks for Large-Scale Image Recognition. And what's famous about VGG is that they use a sequence of only 3x3 convolutional layers throughout its network. I'll give you a picture of the diagram, of the network diagram shortly, but it was very clever and very unique in this design. And it was actually pretty deep by 2014 standards of being 16 and 19 layers, hence the names VGG 16 and 19. And due to its depth and the number of parameters, VGG takes very, very long time to train. I think these researchers took, I think it was 2 weeks using 2 GPUs to train VGG. So it's not something you can actually train on your home system even today, unless we're using GPUs. So this is basically the condensed diagram for VGG. These are the different versions, A, ALRN, B, C, and stuff. E was VGG 19, and I think C or D are different flavors of VGG 16. So you can see the sequence of convolutional layers here. 64 filters each, then it keeps getting more and more filters, 128, 256, 512. And basically max pool all at the end, and then we have all these fully connected layers at the end here. So it's a relatively simple architecture, and I'm pretty sure by now you can actually build this on your own. This might be a lot of layers to add, but you can build this on your own in Keras. So now let's take a look at ResNet 50. Hi, and welcome to chapter 14.3, where we talk about ResNet 50. So ResNet 50 was the winner of the ILSR VC competition in 2015. It was developed by these researchers here, And res in ResNet stands for residual network, and that's because it uses the concept of residual learning, which helps it in a number of ways, and I'll talk about those ways now. So the beauty of ResNet was that it got around the problem of just instead of making networks deeper and deeper, which was the trend back in 2015, and by doing that, by making it deeper and deeper, people were coming across accuracy becoming saturated and then degrading rapidly during training, which was not good. So what ResNet did was that it introduced a shallower architecture with a deep residual learning framework. And ResNet, instead of learning low, mid, and high level features, it learns residuals by using shortcut connections, directly connecting the input of the nth layer to an n plus x layer. So this results in far easier training and resolves the degrading accuracy problem. This is what the ResNet residual module looks like here. Okay, you can take a look. Basically, this is an x1 layer here, goes through these layers here, and is added back to the x plus 1 layer here. So now let's move on to Inception version 3. Hi, and welcome to chapter 14.4, where we take a look at Inception, or the Inception models. And if you're familiar with Inception, the movie, you may be familiar with the Inception model concept. So the Inception architecture was introduced by Szegedy, pronounced it right, hopefully, in 2014 with his paper titled Going Deeper with Convolutions. And in the Inception model, at least version 1 of it, was the winner of the ILS VRC 2014 competition. And it was implemented, the model was actually implemented by Google Linux. So that was a Google Research Group team. And since then, further improvements have been made, so we have Inception version 2 and 3. So now let's move on to what makes the Inception model special, okay? So the beauty of the Inception model is that it is a concatenation of multiple filter sizes. So instead of having one filter here, we actually have 4 filters in a series, or basically parallel, I should say, between here, these layers. So that's a unique architecture that we haven't seen before. Before, we had totally sequential models that were just like one filter feeds into the next filter, well, actually at least one layer feeds into the next layer. However, now we have these 3 convolutions here to combine with a max pooling at the end here. And what this means here is that number of parameters in the Inception model was much less than VGG 16 and 19, which means that it was much quicker and faster to train. This is how the architecture actually looks. These basically parallel layers here are the concatenated multiple filter sizes that we've seen here before. And basically Inception is just a sequential sequence of these parallel filters over and over here. You can take a look at the paper here. It's quite good to read these papers because you get very familiar with advanced CNN concepts. So that concludes these chapters on these models. I hope you found them informative. They were a very brief overview, and even I myself don't understand a bunch of these models in that detail. I used to know Inception and VGG quite well. Honestly, don't know that much about ResNet. However, I will read the paper, so if you have any questions about ResNet and the rest of these models, feel free to ask me in the course comments. Thank you. Hi, and welcome to chapter 15, where we take a look at transfer learning and fine-tuning, 2 very important concepts that will help you immensely in training your CNNs. Okay, so let's take a look at the contents of this chapter. So in 15.1, I explained to you what exactly transfer learning and fine-tuning are, and then we use these concepts to build a flower classifier using VGG16, and then we actually built a monkey breed identifier using MobileNet and transfer learning. So it's going to be quite cool, so stay tuned. Hi, and welcome to chapter 15.1, where I explain to you what exactly is transfer learning and fine-tuning. So, as we know from before, training complicated and deep CNNs is very slow. AlexNet and VGG in particular are deep, parameter-laden networks. VGG alone has 138 million parameters, and ResNet 50 has 50 hidden layers. So despite having less parameters, it's still a lot of layers, so it takes some time to train. So while these networks attain relatively excellent performance on ImageNet, training them on a CPU is definitely not recommended. You are not going to get anywhere close to good results, even training for a month on a CPU. So these CNNs are often trained for a couple of weeks or more using an arrays of GPUs. That's to tell you how complicated and how long it takes to get good results on ImageNet. So what if there was a way we could reuse those pre-trained models and make our own classifiers? We've seen Keras actually ships with pre-trained models on ImageNet, and those models were the models I showed you before in chapter 14. And these weights are already tuned to detect thousands of low and mid and high level features. What if we can use these already trained networks now to build our own classifiers? And well, we can. Introducing transfer learning and fine-tuning. This solves the problem we just explained. So let's talk a bit about transfer learning and fine-tuning now. So fine-tuning. The concept of fine-tuning is often and justifiably confused with transfer learning. However, it merely is a type of transfer learning. Fine-tuning is where we take a pre-trained deep CNN, so one of those like ResNet or VGG as we've seen before, and we use the already trained, typically on ImageNet, model to aid our new image classification tasks. Typically in fine-tuning, we are taking an already trained CNN and training it on our new dataset. Okay, so basically what I'm saying, which I'll explain shortly, is start over. So let's take a look at these concepts. Firstly, let's talk about fine-tuning. Now, the concept of fine-tuning is often and very justifiably confused with transfer learning, and that's because it's very similar and it's merely a type of transfer learning. Fine-tuning is where we take a pre-trained deep CNN and we use this model that's already been trained, most likely on ImageNet, to basically assist or aid our new image classification tasks. And typically in fine-tuning, we are taking an already trained CNN and training it on our new dataset. So what we do is we then freeze the lower layers of this model, and I'll illustrate to you what this means shortly. And we train only the top or fully connected layers. And that's how we actually train it on our new model here. So effectively, we're just replacing the class outputs of an already trained model. And sometimes we can actually go back and unfreeze the lower weights and train them again to get even better performance. So let me explain this to you illustratively, what's happening. So imagine this is a deep, much deeper than this, but imagine this is a deep CNN that's already been trained. All right? So when I say we freeze the lower layers, we're freezing all the convolutional layers from between the input and up to the fully connected layer here. So these weights imagine these weights have already been trained, and they're very good at picking up high, low, and mid-level features. So what we do now is we just basically change the classes that we want for our model, and we basically just manipulate the top layer and train it on our dataset now. So this is the frozen part here, and this is the part we have basically modified and unfroze, and are going to train this part separately. So in fine-tuning, in most deep CNNs, the first few convolutional layers learn low-level features, as I explained. Those are like things like edge detectors or color blobs and that kind of stuff. And sorry. And as we progress through the network, it learns more high and mid-level features. So in fine-tuning, we just keep the lower levels frozen, and we can also just train the high-level features as well. So these are the steps here. Pretty much just went through this for you. But basically we freeze the lower layers, then we add or modify our own fully connected layer, and we use a very tiny learning rate, and we just initiate training again. It's quite easy to do in Keras. I'll get to that code shortly, and it's quite powerful. By using these already well-trained models, we can get superbly good accuracy on new image tasks. So what about transfer learning? Now, as we've seen in fine-tuning, we have taken an already pre-trained network and trained it, or segments of it, on some new data for a new image data classification task. All right? So transfer learning is pretty much almost the same thing, and a lot of researchers and a lot of people in the industry use these terms interchangeably. However, what transfer learning really implies is that we're taking the knowledge learned from a pre-trained network and basically applying it to a similar task, and therefore not really retraining much of the network. So what that means effectively is that, let's go back to this diagram. In fine-tuning, The reason why we call it fine-tuning for is that we can actually train these layers here. So in both transfer learning and fine-tuning, we're basically unfreezing the top layer here and modifying it for our classes. But in fine-tuning, we can tend to go back and train this layer here. That's pretty much the core difference. So here's a quick quote from the deep learning book. I'm pretty sure you can click this link on the PDF slides that I give you. Basically, transfer learning and domain adaptation refer to the situation where what has already been learned or what has been learned in one setting is now exploited to improve generalization in another setting. That's effectively what transfer learning means. And we're going to do some practical examples now. We're going to use MobileNet to create a monkey breed classifier, and then we're going to use VGG to create a flower classifier. So stay tuned and we're going to have some fun with these models, I guarantee it. Hi, and welcome to chapter 15.2, where we're going to build a monkey breed classifier and basically use the concept of transfer learning to get very high accuracy very quickly. So let's take a look at this data set. This is where it was taken. It's taken from a Kaggle project. And basically it has about 80 images, I think, of about 10 different types of monkeys each. These are the species of monkeys here. And actually, sorry, not 80, 131 to 152 images of each class. And these are some sample images here. And you'll notice that some are quite small and at different aspect ratios. Images are various sizes and quality as well. So it's pretty much like what you might build as your own data set, effectively. It's not well standardized, not super neat, not super high quality images, just random images taken from the internet. So now let's move on to our IPython notebook and begin creating this classifier. Okay, so before we begin, I hope you downloaded your resource file, your monkey breed dataset, and have placed it inside of this directory here. This is the transfer learning directory, so you have the monkey breed directory here with our training images, and each one is in a folder here. And let's go back, and now hopefully that's set up correctly for you. So now we can go back. Sorry, went back too far. And let's open up this here. I already have it open right now. So I'm going to go through this step by step so you understand exactly how we can apply transfer learning. All right. So we're doing this with MobileNet. And the reason I've chose MobileNet for is because it actually trains quite quickly on CPUs. So let's import MobileNet here. And then let's define the image rows and columns. So we're going to use uniform square images that are 224 by 224 in size. And this is how we basically define MobileNet when we load it in. We want the weights to be ImageNet. We've seen this before in our pre-trained model section. However, we haven't seen these parameters here. I'll quickly discuss this with you. What we're going to do is that we're going to include the top and set this at false. What this means is that the fully connected layers, the last layers at the top of the model, are basically not included in the model. So I'm going to show you how that looks pretty soon. And input shape is a standard thing. We just define the input shape of this model to be this. That's why we define these parameters up here. And tree means color depth of tree, RGB. So this is a cool thing we can do with Keras models that we load. So we have our model here called MobileNet. So by addressing the layers, MobileNet.layers, this returns an array, and we can basically loop through these arrays here and actually turn off manually the parameter or the flag that controls whether this layer should be trainable or not. So what we do in this 2 lines of code here is that we're basically setting all the layers in MobileNet to be non-trainable, basically fixed. This is how we freeze the weights right here. So now we can actually print these layers here, and basically what we're printing is the name of the layer, this number I, as we go through the loop, and we're going to print the flag layer.trainable, whether it's trainable true or false. So you're going to see all the layers now, which is quite a bit from MobileNet, are set to false. So this is pretty awesome already. So I hope you're following. Simple code so far. So now what we're going to do is that we're going to create a simple function here that basically adds the fully connected head back onto the model we loaded here. Because remember, we loaded it, but we didn't include the top. So now we have a model without any top. So now actually I want to show you something quickly. What if we set this to true? All right, how would this model look? So we saw we had 86 different layers here, last one being ReLU. So let's now print this and see how this looks. It takes about 5 to 10 seconds to run. There we go. Ah, good. So before we had up to 86, now we see we have, basically this is the top fully connected head. This is what we left out before previously. So now let's put it back in, okay? Because what we're going to do, we're going to add our own head here. These are the layers that we're going to add onto a model now. So how do we use this function? This function takes the number of classes for our data set. We specify how many classes we want. So for our monkey breed data set, it's going to be 10. And the bottom model is basically this model here, MobileNet, with all its frozen weights. So let's quickly see what this function does. It takes the bottom model here, and gets the output part of it here, and we create basically the top model now. So what we do now, we've defined the top model like this here. And now the top model, we just simply basically add these layers here. This is a different way of adding layers now on Keras. So we add it and address it to the top model here. So first we do global pooling 2D. We do a dense layer with 1028 nodes. That again, another dense layer here. And then we do a final dense layer with softmax for the 10 classes we want. And then what this does, we return the model, top model, back, okay? So now what we do below is that firstly we just load all our layers that we need and define a number of classes, but now we can actually use our function here where we actually just enter the number of classes, we enter the MobileNet model that we created, that we loaded before, and we add the top, that's the FC layer we defined here, to this model, and that's what we call it FC head. And then what we do now is that we use this Keras model function. So we use it now to get the inputs here, which we define as a MobileNet model, the outputs being the other part of the model that we're going to train, and basically this combines it into one model now. One model where it looks like this when we print it out. It's a lot of layers, as you saw before, 86 layers, but now we have 6 more layers now, these that we defined here. And that's going to show up right here. So this is pretty cool. And look at this here. So we have 5 million parameters, 5.8 million actually. And the trainable parameters are only 2.6, and the non-trainable parameters, which are the weights that we froze, are 3 million. So effectively, we've taken a model that was pretty complex, not super complex like VGG and a couple of the others, but complex enough, and we've made it into a much simpler model to train. So let's get to training our monkey breed dataset now, or training our monkey breed classifier. So we load a dataset using image data generators that you've seen before. We do the standard thing here, which you should be pretty familiar with by now. And then we define some checkpoints, some callbacks, sorry. So we use early stopping and checkpointing here. And then we train for only 5 epochs for now. That's because we don't want it to be take too long. I'm actually training it separately in this window here. So I've actually already trained almost 5 epochs. Didn't realize so much that time flew. So look at this here. You can see after the first epoch, which took just under 5 minutes, our validation accuracy was 88% already. That is actually pretty damn good for such a short space of time. Now in the second iteration, because it's such an early start to the training, even though the training loss is much lower, the validation accuracy is a little bit less, 84%. That's okay. We can sort of live with that. We'll just let it train for more epochs and see how it evolves, because training these pre-trained models when some of the weights are frozen is a little bit different than how we train the CNNs. They basically do effectively converge and get a very high value. However, you do sometimes see some odd fluctuations like this. And look, we have it back up to 91%, 90%. If we wait a few minutes, about 30 seconds at least here, we can actually see what the validation accuracy is at the end of the 5th epoch. So let's wait and see how this looks. One thing to note is that you can actually see our callback, our early stopping callback, actually telling us how validation loss did not improve. So if we left this for 10 epochs, and we had, actually it was here as well, so basically No matter what, this is going to be the last epoch, because I'm pretty sure I set my patience to 3 here. Yep, I usually always do. So right now what it's doing here, the reason why it's stuck at 2 seconds, even though 2 seconds would have passed by the time I started this sentence, is that it's predicting on the training or validation dataset now. That's something that a lot of beginners don't know. Like, they see it pause at the end and be like, oh no, it's stuck. It isn't actually stuck, it's just waiting to run on the validation dataset now. So it takes a little while though, honestly, because sometimes our validation datasets are quite big. Ah, there we go. So look at this. We got 93% accuracy in such a short space of time. So this is quite good. So now let's actually go back to this main page here. Let's load our model, which takes maybe about 10 seconds. And what we're going to do once this model is loaded, we're going to basically use OpenCV, this messy bit of code I wrote here quickly, that loads the images here and runs it through our predictor that we just loaded here. And it's done already. And we're actually going to see the monkey class, see how accurate our real, if our classifier really is 93% accurate. So let's find out. There we go. So this is the true class, Bald Ukari. Guess that's like a Japanese monkey. Okay, so firstly, it got the first one wrong. This is what our model predicted, white-headed capuchin. And no, it was not a white-headed capuchin. Let's see if it gets the others right. Yeah, it did. It got this one right. Pygmy marmoset. Let's see what the others. Nilgiri langur, definitely correct. Pygmy marmoset again, got it right. Got it right. Got it right. Got it right. Got it right again. Got it right. So, seems pretty good. So aside from the first one, our model got basically 9 out of 10 right, which kind of corresponds to a 93% accuracy we got here. So you've just learned to create a model, basically a trained model using transfer learning, and you see how simple it is. You just basically load it with the weights being frozen and the top being not included. Then you build a function to add the top, whatever top you want to add. You can add it in here. Always make sure the last layer is the number of classes you have in your dataset. Then you basically concatenate and compile the models here. Or combine the models, I should say. You do your image generators, define your checkpoints and callbacks, compile, and there we go, and train. So it's really very simple, and I hope you found this chapter quite useful. Thank you. Hi, and welcome to chapter 15.3. We're about to build a flower classifier, and we're going to use transfer learning to do this. So let's take a look at how we actually, or what is our flower classifier, our flower dataset, I should say. So it comes from the Oxford University's Visual Geometry group. It's called Flowers 17, and that's because there's 17 categories of flowers, and there are 80 images in each class in this dataset, so not that much. So this is some sample images from the flower classifier, the Flower 17 dataset. This is the web page from Oxford University, and this is the link you can go to if you want to download it from there yourself. Or you can use the link I have on the left here on the Udemy side panel. Please use that link to actually download it, because I've already pre-processed the data into a format that is easily imported into Keras. If you download it from Oxford University's site, you're going to have to do your pre-processing yourself, and I don't think, if you're a beginner, you're not going to find that fun at all, although it's a good exercise to do sometimes. So anyway, our approach to this problem is that we're going to actually use a pre-trained VGG16 model with all of its weights frozen except the top layer, and we're only going to train the top head of the model with a final output of 17 classes. So let's go back to our IPython notebook and get this done. Okay, so welcome back to our virtual machine. I hope you downloaded the flowers dataset and extracted it to this folder here. That's this folder called Transfer Learning and Fine Tuning, and placed it right here. So we can quickly just inspect it, taking a look at some of our flower pictures. Let's put it on thumbnail view. And yeah, this looks quite nice. So as you can see, we don't have that many images in this dataset. So let's see what kind of accuracy we can get with transfer learning on the VGG model. So let's go to it here. So now let me just close some of these windows that are open. And let's quickly go back to this one here, so you can actually see how I do it. So it's 15, and we go to making a flower classifier. That's this file here. So now that we're in the file, let's take a look at what's going on. So we import the VGG model. That's easily done here. VGG was designed to work on 224 by 224 pixel image input sizes. So let's keep the standard size and go forward. So let's load the model without his weights, with the weights of ImageNet and without the top layer, I should say. So we do that, and let's just print out the layers in this model, okay? So as you can see, default, actually let's load it here. And by default, all the layers are trainable true. That means the default of when you load VGG, all the weights are trainable. So we now have to set this true to false. So that's what we do here. So we load it without a top head with the ImageNet weights, and we set all the trainable layers. We set this flag to false. So let's do this quickly. And that's done there. And now let's create the function where we add our fully connected head. This is where the layers we add now back to the top of our VGG network. Notice this is different to the layers we added in the mobile network. And that's because VGG has a different design to MobileNet. So you're going to have to look at the final design for VGG and replace these layers here. And this D here, this dense layer, this number of dense layers, dense units here, by default we're going to use 256. However, this function allows us to specify it in here. We could add 128 and it would be 128 units here. So let's leave the default. Alright, and then we set the dropout, we set these things. We input our number of classes, which is 17, from the flowers dataset 17. 17 should make sense to you now. And we just concatenate the models here, well, the parts of the model, to get the full model, and then print it out. So let's take a look at it. And we see there are 14 million parameters. It's less than VGG 19 and 16. Sorry, VGG 19. And with trainable parameters, only 135,000. That's quite good. So let me just run this so we have it fresh. And now we just do our data generators here to the flower validation and flower train folders. We set our batch size. We can go, actually let's keep it at 16. All right, and keep going here. So now we declare our callbacks right here. And we just create a callback array, which we pass in here. And let's run this now. So I'm going to leave you to run this. I have run this already, and it takes quite some time. But what I want you to observe is look at the validation accuracy. In 25 epochs, the highest we get was actually 95%, which is quite good. So let's keep going. See, did it ever pass 95? 93 at one time. So this is quite good. So we've got 95% accuracy using transfer-learning, using VGG 16 in transfer-learning. So let's keep going. Let's see what else we can do though, okay? So this section here, can we speed this up? So let's try resizing the images to 64 by 64. Remember, it was designed to work on 224. Now let's do this to 64. So let's change this comment to setting the input size now to alright, and do the standard thing where we load it with the ImageNet weights. We don't include the top, specify the new shape, and we make the layers train we freeze the layers. So that's good. So now let's move on to this. Let us actually start training this model. So as we can see, this model has a different input size. And let's see what we get. So I've trained this before, so you don't have to do it. So what I want you to see though is that what's happened here. Previously before, I actually did not use the callbacks. I left it in view, but I should have done it and I forgot. But what I've done now is for this one we do. So we see some callbacks, feedback from early stopping. So we see it's not increasing, it's monitoring, the patience is good. So at the end, epoch 12 is the one we use. So let's go back to epoch 12. Passed it again. That's this one, 82%. So 82% was our best, lowest validation loss and our best accuracy. So you can see by resizing the images to 64 by 64, which is a substantial decrease in size, to 224 by 224, we got 82%, sorry, how much was it again? Sorry, 82% accuracy. So that's not too bad, to be fair. Actually, sorry, 86% accuracy we got. That was 50.5652. Right, so that is actually this one. So yeah, so this is good. It's not great, but it is pretty good. Hi, and welcome to chapter 16, where we get to design our own customized CNN, one we're going to call Little VGG. So in this section, we first introduced the concept of how we developed Little VGG. And then in 16.2, we're actually going to use Little VGG to do some Simpsons character recognition. So I hope you're looking forward to getting started. Let's get into it. Hi, and welcome to chapter 16.1, where I introduce Little VGG, our own customized VGG network. So, Little VGG is basically a downsized version of VGG 16 or 19. And remember, VGG-inspired networks all use a series of 3x3 convolutional layers where the number of filters just increase as you go further and further into the network. So let's take a look at our Little VGG network diagram, or network architecture. So this was VGG 19 and 16 here. So what I've done, VGG, or VGG 9 you can call them, has 9 weight layers, and basically this is how it lines up compared to this one here. Alright, so we have our first convolution layers here with 64 filters, our max spooling, then our other layer here with these convolutional layers with 128 filters, and then this one here, however, we don't have as much, we just have 2. And then we have our max spooling again, and then our fully connected layers. So we stop here. We don't go on to these deeper layers here, like even VGG 11 does. So we just stop at the 256 kernel count of this last convolutional filter, and then we get straight into our FC layers. So this is our number of parameters here. So let's build this in Keras. And then we get to use this on the Simpsons training, on the Simpsons character dataset. So in section 16.2, we're going to use Little VGG on our Simpsons character dataset to do some Simpsons character recognition. This is going to be pretty cool. So this dataset was sourced from Kaggle. Here's the link to it. And it actually came with more classes than this. However, I limited it to 20 classes of the most popular characters. And there are about 200 to 400 RGB pitches in it each, all of which are different sizes and orientations and aspect ratios. And the images were of, yeah, I just said that, so that's fine. But however, it's good to know that even though some images have multiple characters, some of the images, basically the main character is the focus of it. So let's take a look at some of the images here. So this is what I mean, by the way. Like, Lisa is definitely the main character here. However, there are other characters here. So that may confuse our classifier, but let's see how it performs. Okay, so we're in our virtual machine with our IPython Simpsons notebook open. Let me just direct you to how we got into here in case you're a bit confused. So it's chapter 16 here, design your own CNN called Little VGG. And I hope you downloaded the dataset in the resources section of this file, of this chapter, and place it right here. And again, just always check the folders to make sure your images are here. So we have our characters, our classes, and basically let's go back to this file. Alright, so let's have them open here. So now, basically, you've seen the standard way we do things. Alright, what I'm going to tell you about here though is that we're resizing the images to 32 by 32 pixels, quite small. So let's see how it performs though, okay? So we're doing some data augmentation, the same usual things we do, rotations, width shifting, horizontal flipping, so we kind of get the characters, we add some variety to the characters, and then we declare our generators here, and then this is the part I want to show you. This is where we build our little VGG model, alright? So I believe you remember from the diagram I showed you in the slides that this is how it's defined. So we have our 2 convolutional layers here, 64 filters each, and all the filters, all the kernel sizes here are 3 by 3. This is typical of VGG family model, alright? So we have these convolution layers here, then the second set here, and then another set here. These are the ones with 256 filters. And then we have our final FC dense layers here with some dropouts. We have 2 sets of dense dense connections here. And then we finally go to our number, our softmax classifier with number of classes, which is 20, which we defined up here. So let's run this. Actually, let me run the first one. There we go. And then let's run this one here. So good. So we just display our model. It's quite a number of layers here, but it's luckily this is a substantially smaller model compared to VGG16. This is only 2.2 million parameters. And if you want to take a look at our model, we can plot it. Remember how we did this earlier in the earlier chapters? So this is a